Hi, this video is going to be about measuring the performance of various USB power cables. The idea of this came about from when I was doing my Seed Studio Fusion PCB review. That's up on my blog. But one of the things I did is I manufactured a new board for my standalone MIDI player. And the new board had a 3.5 millimeter power plug in the back of it. So the idea is I could use this 3.5 millimeter power cable, nice one here, with a switch on it, to power this off of the USB port. Previously I'd just been using a USB cable to the Pi. I like the barrel connectors better. But I went to go try this out and it didn't work. The Raspberry Pi, it had some lights that just sat there and blinked. It wouldn't boot up. I couldn't SSH to it. I'm like, what's wrong? Did I actually make the PC board wrong? Did I short something out and ruin the Pi when I was building this? Then I got the idea, maybe it's a problem with the power cable. So I went back and I plugged in the good old USB cable. This one here, and it booted just fine. So sure enough, it turns out that this power cable that I bought on eBay had way too much voltage drop, and it could not power my simple little Raspberry Pi project. Okay, to get an idea of what the current draw is on my Raspberry Pi project, I'm going to use this Mushi meter. So I've reviewed this before. So the Mushi meter is a multimeter that interfaces to your iPad. So my probes are hooked up to it, and it's going to send wireless signal to the iPad. And the iPad will graph the volts and amps. So volts are going to be in green, amps are in red. So I've got the Mushi meter hooked up. I'm going to plug this in. Let me restart this. So right now we're just seeing some random noise. Let me plug in the project. Now we're seeing actual data, so volts is in the green, amps are in the red. So we can see as it boots up, lots of things happen with the current. We've got some various spikes as the Raspberry Pi is doing its initialization. We peak somewhere around 600 to 650 milliamps, and then there's a steady state about 450 milliamps. And as it does other things, we might see additional spikes in the graph, but we know that if we can't sustain this 600 milliamp spike during boot, the thing is not going to be able to boot. It's going to get up there, draw too much current, and then it'll, brown out and reset, which is kind of the behavior I was seeing that led to this whole investigation to see what was going on here. So that basically gives us a characterization of the type of load that we're going to have to support. So let's take a look at that and test out some various power cables. So I've kind of built myself a jig here to do all this testing, and some little fixtures. Got some little breakouts that break out various jacks, USB a female connector so we can power USB cable. You do have to be careful of your banana plugs. As reported in other blogs, there have been some cheap banana plugs that get corroded and they will glitch your measurements up. I have checked these ones, although they are cheap, they are working fine. That may just be because they haven't been used very much and the gold plating just hasn't rubbed off of them yet. So won't be a banana plug failure today, I don't believe. But anyway, let's hook some things up. So this is going to be our source. This is going to be my power supply. It's my benchtop. It's a switching power supply. It's my favorite because it's nice and small. It's currently set to deliver 5.05 volts at up to 3 amps. On this end, we have my DC load. Now this I built based on a video I saw on the EEV blog, video blog, that told you how to build a DC load, basically out of spare parts, a MOSFET, some resistors, and an op amp. So I went ahead and I built one of those, and I've actually used this many times over the years, and this will be, I think, my first time demoing this in a video to show just how useful that turned out. So what we're going to do is on that end, we will put our sink. So we've got a source, we've got a sink. Now we also want to be able to measure the voltage over here on the load side. So we will take and we will plug. Well, let's reverse this. So we can switch these. We'll plug these leads in first. We'll plug these ones to those ones. Then we're going to run this over here to my fluke. Now we take a suspect power cord, plug it in here, plug the other end in here. Let's make sure we can see everything. Let's plug in the power to the DC load. Okay, the DC load is on. Looks like everything's good and visible. This is calibrated to more or less read milliamps. It's not quite perfect. This is cheap eBay panel meter I got. Probably need some trimming to get it exactly perfect, but it's like within a couple percent of what the milliamps will be in the load. We've also got volts and amps over here, so if we turn this supply on, 5.06 volts, 3 milliamps, over there 3 milliamps. Yeah, on the fluke we've got 5.03 volts. So pretty much on a no load condition we're getting, you know, pretty much our 5 volts. Let's ramp up the load. So this is a multi-turn pot. We can ramp up. It's real sensitive down here on the lower end. But there's about 50 milliamps. So we're at about 4.73 volts. That's with just 50 milliamps. So we dropped 0.3 volts just on a 50 milliamp load with this cable. Let's go up to 100 milliamps. So there's 100 milliamps. Now we're down to 4.41. So we've dropped over half a volt now, 100 milliamps through this cable. Let's try 150. Now we're down to 4.11. Let's just keep going. $200 milliamps. We're down to 3.80. Hard to dial it in exactly, but 250 milliamps. We're down to 3.49. 300 milliamps. 17. Do 350 milliamps. 2.86 volts. 400 milliamps. 2.54. 450 milliamps. 2.21. 500 milliamps, 1.87. So after the 500, I'm going to stop stepping it in 50 milliamp increments and go to 250 milliamp increments. So let's go up to 750. We actually couldn't make 750. The voltage down here on this end, it drops so low that my DC load doesn't work anymore. It needs a certain amount of minimum voltage into the DC load for the circuitry in there to apply the load. So here's another one that I typically use. Instead of a 3.5 millimeter barrel jack, this is a 5.5 millimeter barrel jack. Let's use this plug instead. Got a different fixture that goes with that. 5.5 millimeter jack. This one doesn't have a switch or anything fancy on it. It's just a 5.5 millimeter plug. Okay, so let's do the same experiment. We'll start 5.5. Start at 50 milliamps. So you say, well, the other one had a switch. This one doesn't have a switch. Well, I do actually happen to have an inline switch. Let's see what happens. If we add this inline switch, and let's do the 5.5 with the switch. 50 milliamps. Okay, we've got another gizmo we can try here. I'm going to unplug the switch. And what I have here is a 5.5 to 3.5 millimeter adapter. That way I can use my good cable with the little jacks. So we'll hook that up. And let's chart this one out too. 50 milliamps. There's Leia. Yeah, Leia likes to help out with the videos. Wave at the camera, Leia. Down, down, down. Over. Smile. Where's Leia? Where's Leia? There's Leia.
Like, what are we doing?
Where's Leia? We're testing USB cables.
Woohoo!
All right. 200 milliamps was 4.9. 250 milliamps. Okay, let's dial it down. So let's try micro USB cable. Got a fixture for that. Always have a double the time lining these things up. There we go. Micro USB, the long one. Out at 50 milliamps. We've got this PLX retractable one. This came from probably some Kickstarter from PLX devices. Let's see what happens. It's a micro USB. As usual, I have a heck of a time plugging these things in. There we go. And 50 milliamps. And lastly, we've got this shorty cable. See how it does. I tend to use the shorty cable in a lot of my projects. Uh, 50 milliamps, we've got 5.05. Okay, so I have managed to make a big long chart of numbers for all these different cables. I'm going to go plot them into Excel and see what the results look like. Okay, as promised, here's some insight into the DC load itself. This thing is built with spare parts, eBay parts, custom Osh Park circuit board. I'm not going to go into the schematic like I normally would because the EEV blog website already has a video which discusses how to design and build one of these things, essentially out of spare parts, so I really don't need to go into the theory of operation or the schematic, but I thought, I would just show my implementation of the EEV blog design. And what we've got, there's some kind of MOSFET here, big MOSFET mounted to what was a leftover heatsink from some Pentium of years past. So here's the resistor that's used for current sense, that's used for both the meter, and it's used for this LM358, which is going to set the current limit. There's a couple different options. The way Dave showed in his video, I think, was to parallel a bunch of resistors. You want kind of a lot of watts there, so you parallel a bunch of small, high precision resistors is one way to do it. Or what I did on eBay, I just bought this 1 ohm precision power resistor thing. It's heat sinked and soldered that in. There's other things. I think there's a voltage regulator. There's the LM358, multi-turn potentiometer. This doesn't really get very hot. I don't even know if the fan is necessary. The fan makes a lot of noise, kind of annoying. Put a switch so we could switch the load on and off. DC panel meter. Just get those from eBay. Anyway, that's it. So I plotted this out, all of the cables that I measured, so we can see how each one performs. The first thing to notice is these are all pretty linear. What that means is we probably could have computed them mathematically. And furthermore, Ohm's law probably would have led you to the same thing that we managed to measure, but I think it was funner to do it by measure and experimentation. So from the top, this was the short micro USB cable. The next one was the long micro USB cable. It was kind of thick, so we assume it had beefy wire in there. Then we had a cluster together here. The retractable micro USB, the 5.5 millimeter barrel connector, and then the 5.5 millimeter barrel connector with the little adapter on the end of it that adapted down to 3.5 millimeter. Those did pretty good. The two places where we used the switch was like horrible. This here is the 5.5 millimeter barrel cable with the little add-on switch. This thing here, and you can see this add-on switch that just killed the performance of that cable. I mean, it's added some additional resistance in there, and it's not good. The other one, and this is what started this whole project off, was this cable with the switch. This was the 3.5 millimeter one, the one that failed to power my project. We can see, it doesn't even make it to the 600 milliamps, not even close. I mean, it just falls off a cliff there. So obviously this cable here, this is like completely useless. I mean, you can't even get a couple hundred milliamps through this thing without the horrible voltage drop making it worthless. This was picture this on eBay, showed 24 gauge wire. I don't believe it's really 24 gauge wire. I think it's smaller than that. So anyway, these are interesting results, I think. It gives me some good real world knowledge to know which cables will power my projects. Of course, if you encounter cables, they're probably not the same manufacturer, brand, wire gauge as the cables that I encountered, so you would either have to measure them yourself through experimentation, or measure the resistance, do the Ohm's law calculations to calculate your voltage drop. So anyway, I hope this was useful. I hope my measurement methodology made sense. If I did anything here that didn't make sense, please let me know. I think it was a good practical experiment in seeing how these cables perform, and in trying out my DC load, and just having fun. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff.
Bye.